Hello, everyone. My name is Ray Jayavardhana. I'm the Harold Tanner Dean of Arts and Sciences and a professor of astronomy here at Cornell. It is my great pleasure to welcome you to the 7th installment of our Arts Unplugged series. We created these signature events to engage with the broader community and to bring the work and the voices of our terrific scholars in the College of Arts and Sciences into the public sphere for discussion and inspiration. Today, you will hear from faculty members spanning a range of disciplines, including physics, chemistry, molecular biology, philosophy, poetry, and Romance studies, as we explore the science and art of the very, very small. Whether you have an interest in nanoscience and quantum computing, or an appreciation of science fiction and artistic imagery, this event is for you. I hope you will enjoy the program as much as we've enjoyed pulling together all of these brilliant scholars to illustrate how we are working in the molecular, nano, and quantum realms to better understand our universe, and how these emerging discoveries will shape our future. Many of you are watching this event from the comfort of your home through our partner eCornell. We're grateful to the folks at eCornell for helping us craft and share the presentations you're about to see. I also want to thank the Communications and Alumni Affairs and Development staff in the College of Arts and Sciences for developing and promoting the event. We have many Cornell alumni, as well as students from local high schools and members of the general public joining us, and we thank all of you for your engagement. Here on our Ithaca campus, we have live audiences in the Clark Atrium of the Physical Sciences Building and the Gross Family Atrium in Claremont Hall. These participants, including students from the Milstein program in Technology and Humanity, will be trying their hands at making origami bots during our intermission. If you're on campus, be sure to check out our Science of the Very, Very Small art exhibit in the Physical Sciences Building as well. It will be up for the remainder of this semester. Who better to host and moderate this evening than our newest Zubro Distinguished Visiting Journalist, Natalie Volkova, a science writer with Quanta magazine. Natalie arrived on campus last week and will be here through next week, meeting with faculty and students across our science and math departments and touring our research centers and labs like the Cornell Nanoscale facility, where our scientists first brought nanobots to life. We're delighted to have Natalie here to learn about all the great research happening on campus while sharing her insights on science writing and communications with us. If you've not read her fascinating in-depth articles in Quanta magazine, I very much encourage you to do so. She really is an exceptional science journalist. If you're on campus and interested in science communications, you won't want to miss the masterclass on science storytelling that she will be holding next Tuesday, March 15th. You can check out the Arts and Sciences website for more information. Now, please join me in welcoming Natalie Volkova.
We tend to think of ourselves as small in the grand scheme of things, and understandably so. The universe is huge. You'd have to line up 500 trillion humans head to toe to stretch across the observable universe. And yet, somehow, it's still easier to conceive of how much bigger space is compared to us than it is to imagine how small the smallest things in the universe are relative to us. In fact, in the scheme of things, we're on the large side. We're 26 orders of magnitude smaller than the observable universe, but the tiniest objects that exist are 35 orders of magnitude smaller than us. I provide these numbers to orient you to the vast world of the very, very small. A cell is at most 100 micrometers across, so 20,000 times smaller than a human. An atom is 0.2 nanometers across, so 10 billion times smaller than a human. The diameter of an atomic nucleus is 10,000 times smaller than an atom, and a quadrillion times smaller than a human. And each proton and neutron in that nucleus is made of 3 quarks that are smaller still. These are the quantum scales that physicists triumphantly explored over the course of the 20th century. They learned that the atoms and subatomic particles that exist on these scales play by different rules called quantum mechanics. The particles are probabilistic, which means they have some probability of being over here and some probability of being over there at the same time. And when they interact, no one can predict the outcome, only the probabilities of different outcomes. In the 1930s, physicists developed quantum field theory, a more sophisticated description of what's going on that casts particles as little localized excitations in fields that permeate all of space. Gradually, physicists discovered more and more of these particles and fields and worked out their relationships. A quantum field theory called the Standard Model of particle physics, completed in 1975, gives an extremely accurate description of the 17 known elementary particles, including all the building blocks of atoms. But there are smaller scales still. The Standard Model treats particles as structureless points, but if you zoom in on the points far enough, additional structure may reveal itself. For instance, you might see that there are little vibrating strings, as one of today's presenters will talk about. And at that scale, space itself would not be the smooth continuum that we're familiar with, but rather will dissolve into something else. We're going to hear today not only about the exploration of nature's smallest distance scales, but also what they can do for us. In 1959, the physicist Richard Feynman gave a famous lecture called "There's Plenty of Room at the Bottom." He was essentially brainstorming possibilities in nanoscience. He imagined building nanoscale machines that can arrange atoms one by one to build dense computer circuits, synthesize chemicals, and even do medical interventions. Nanoscience wouldn't start to actually take off until a few decades later, in the 80s and 90s, when various kinds of microscopes were invented that could go beyond optical microscopes and start to allow researchers to resolve atoms and molecules. Then progress could start taking off. We'll hear today about where the progress has led so far. After each segment, I'll be talking with the presenters to dive deeper into the questions they raise. After all the presentations, it will be your turn to ask the questions, so we hope you'll participate. You may submit questions in the chat, which you can open by clicking the dialog box at the top right of your video player. Throughout our discussion, we'll be sharing URLs and resources in the chat as well, so look out for those. If you're watching the archived recording, those links are available in the overview section just below. We're going to have a fun activity around 5:30 p.m. that involves origami. So if you don't have origami paper at home, please go to the link below. There you can find a template to download and print out to create your own Science of the Very, Very Small origami paper. This event is being recorded and will be viewable at this same URL afterward. And now for our first topic, walking nanorobots.
We're interested in making robots so small that you'd need a microscope to see them. To make these robots, you have to completely reimagine and redesign the process of fabricating these machines. So what's involved? Well, essentially a robot is composed of two parts, a brain and the actuating limbs. Now the brain, believe it or not, is actually simple because 50 years of Moore's law has solved that problem. We can now make microcircuits that are so small that they could fit really easily on the kinds of footprints that we're talking about. The legs, on the other hand, are a major challenge. So a group of us had this idea that maybe we could steal the fabrication tools that are used by the semiconductor industry to build the chips and then build the robot around the chip and then fold that robot into the three-dimensional shape that we want to make. Now, if you're going to start doing origami at the microscale, you're only as good as the paper that you can manufacture. And one of the things that we had to learn was how to take advantage of the unique tools at the Cornell nanofabrication facility to create the world's thinnest paper, including a single sheet of graphene that we could cut up into a kirigami device, or these nanometer thin sheets that you're seeing on the right and the bottom. If you're going to be making origami at the microscale, there's really two strategies. One is to shrink the origami artist, and that we still don't know how to do. The second is that you could have the paper fold itself. Here it is. This is a sheet of paper that's only 10 nanometers thin, folding itself. How does it work? We start with a 7 nanometer thin platinum layer. We coat one side of the platinum with an inert material like titanium dioxide. We then fabricate the device that we want, and when we put it in solution and put a voltage on the platinum, we can get ions that are dissociated in the solvent to adsorb onto the platinum surface. When that happens, you create a stress that bends the device. If you now apply the reverse voltage, you can drive those ions away and the device returns to itself. If you put stiff elements, you can restrict the bending to occur where you want, and now you have an origami fold. We can now make devices that are only about a footprint of a hair diameter and can still fold and unfold, like this duck that you're seeing on the very right. This particular design graced the cover of Science Robotics this past March. As amazing as it is, there's still a little defect, which is that stupid wire that's hanging out from the bird on the left side. And one of the things that you can do in order to avoid those wires is put the power source on the device itself. So this is how we do it. You essentially create a photovoltaic or a solar panel and connect that up to the actuator so that when you shine light on the solar panel, it moves the limb. Now, this was our first ever Hello World. This is where we start getting really creative, putting photovoltaics for the front legs, photovoltaics for the back legs. We make bajillions of these devices and then put the pads on to restrict the bending so that we get exactly the folds that we want to actuate. And with that, you can create what we lovingly call Brobot. Brobot is here flexing his muscles. He has chest hair and belongs on a beach somewhere. But you can get the basic idea of what we're talking about here. You shine light on the front photovoltaics that actuates the limbs. Now, as amazing as Brobot is, he also has some defects. That chest hair, the technical term for that is schmutz. Clearly, we ripped off its back legs. But if you work hard to solve these problems, you can create what is now the world's smallest walking robot, a 40 micron by 70 micron by 2 micron thick robot that folds itself up and walks off the page. The way this robot works is that we shine a laser on the front photovoltaic to activate the front legs and the back photovoltaic to activate the back legs. And in that sense, this robot, as amazing as it is still just a marionette being controlled by strings, in our case, laser pulses that are moving each limb. How do we go beyond that? We are working now with a commercial foundry, XFAB, to create microchips that would go on these robots. In this particular case, I'm showing you a microchip that acts like a clock circuit. On the second image, you're seeing a wafer full of these microcircuits. We tested that it works right, and now we can use it to drive the robots without shining lasers at specific photovoltaics. This thing has a brain that coordinates the limb movements and gets the robot to move on its own. This is the moment where we cut the strings to the marionette and Pinocchio comes to life. And here you go. This is Antbot. It uses a hexapod gate, so a tripod on one side and a tripod on the other to move itself forward. And all we have to do is put this robot in sunlight and the brain does the rest of the coordination. What could we do with these kinds of robots? Well, basically anything you can imagine doing at the macro scale. Clean surfaces of bacteria, or use them to build different components, transport cargo from one location to another, maybe conduct microsurgeries, or explore new worlds that are inaccessible when you look top down using microscopic techniques. Projects like these can only happen when you get a whole crew of students, postdocs working in various labs in a coordinated fashion. And that's exactly what works really well here at Cornell. We're interested in making robots so
Thanks,
small
Utai. Fascinating.
that you'd need a microscope.
When you were trying to figure out how to fold a flat sheet into different robot shapes, did you have to actually study origami folding patterns? And if so, could you talk about that process of learning those folding principles?
Yeah, so the dirty little secret here is that I actually know very little origami. But what the NSF did when they started these programs was they had grants where we could pair up with origami artists. And this was extremely valuable because it let people who have sort of, hands-on knowledge of origami get together with scientists to do things that neither of us could do on our own. Now, as we've gone further, what I've noticed is that actually many of my students know origami. Origami seems to be a way into science for many kids, and a very powerful tool for sort of sparking the imagination. And so I've relied a lot on the origami folding skills of my students and the collaborative artists that we work with to make the designs that you see.
Cool. So you also talked about sort of working to make the robots autonomous by attaching microchips to them. Can you say a bit more about like how the microchip drives the robot? In particular, like, is the robot responding to its environment in some way, or at this point is it sort of executing pre-programmed code?
Right. So the current robot, Antbot, is executing basically the result of a timing circuit. So we have a little clock on the robot, and every time the clock hits a particular point in the cycle, it fires one of the legs and causes it to move. So by changing the phases of when the legs fire, you can get the locomotory patterns that we're talking about. That's just a simple clock circuit. Now, a more interesting robot that we've made is called Dogbot, and it can receive commands. So you can send a pulse of light, Dogbot, and it will essentially be able to respond by speeding up its gait or slowing it down. Now, in the future, we envision that these robots will be able to sense their environment, maybe chemically understand something about the pH of the solution around them, or whether there are other chemicals around them that they want to swim towards. And mechanically, they'll be able to have little whiskers that allow them to sense their environment very much in the way that cockroaches use the whiskers to run across or run next to a wall and maybe detect their position from that wall. And then finally, we want these robots to be able to communicate with each other. And so we're envisioning trying to work on ways for the robots to transfer information between one another. And that becomes interesting because now, even though each one of these robots by itself might be a very simple computer, if you combine all of them and allow them to share that computational power in something much more sort of complex, might emerge in terms of their ability to control their environment, respond to it, collectively sense chemicals, and then manipulate their environment to get something that you couldn't get with one robot on its own. And that's something that we're very well positioned to do robots, because we're building these robots using these fabrication techniques that where we can fabricate them in parallel on massive scales, hundreds of thousands of robots per wafer.
Oh, exciting. Looking forward to hearing more about that in the future. So now on to our next segment.
Hi, everyone. I'll be talking about CRISPR for the next 5 minutes. So you may be wondering, I've heard about CRISPR before. These are molecular scissors. They're guided by a magic molecule called RNA. And they can do genome editing. And I've also heard that the pioneers in this field have won the Nobel Prize. And indeed, they won the Nobel Prize in 2020. And these are two women scientists, Jennifer Doudna and Emmanuelle Charpentier. So all these answers are great. And if you're in my class, you would have gotten full points. And so you would got bonus point if you further point out that CRISPR is an RNA-guided immunity system used by bacteria to fight off viruses and mobile genetic elements. And so they cut and paste short pieces of DNA into the CRISPR array to establish a molecular memory. And there are various different kinds of CRISPR systems, and they do the following steps slightly differently. So in my favorite system, which is called Crispr Cas3, many proteins assemble with the guide RNA to form a complex called cascade. And so the job is to use the RNA guide to find the matching DNA target. And this is done by unzipping the DNA into two strands and then promote the formation of heteroduplex between the DNA and the RNA strand. So afterwards, my favorite molecule, Cas3 enzyme, is recruited by Cascade. And so this is a really powerful nuclease. And so upon recruitment, it's going to nick the DNA and further travel along the DNA and shred the DNA into pieces along its path. So as you can see, there are many moving parts, and it's a very, very sophisticated system. And so I just felt fascinated by the system because it gave me a feeling that this is almost like my childhood clock. So my lab spent many years basically trying to provide a molecular dissection of the system. We inspected the system at nanoscale and generated many publications. And so what's different between the fate of my childhood clock and the Cas3 system is that after the inspection, I was actually able to successfully put it back into one piece and put it into the human cells and demonstrated that we can use it for genome editing. So kilobases of DNA can be deleted from a human genome in an RNA-guided fashion. The experimental outcome agrees with our mechanism model quite well. And this is always a good thing when experiments agrees with the model. That means we're on the right track. So our conclusion in the first half of the work is that CRISPR Cas3 is a high-efficiency, high-fidelity deletion editing tool. And so then in the next phase of study, we really wish to bring its therapeutic power. And we have a few ideas in testing. One idea is about applying CRISPR Cas3 for antiviral applications. So most viruses, when infecting us, only give temporal discomfort, right? So, but some viruses will persist, and so they cause lifelong infections. And this is because they either circularize their genome to become more stable, or worse yet, they integrate into our genome and become part of our own DNA. So none of these cases are welcome. And in fact, HIV used the second scheme, and it's extremely hard to eradicate HIV genomes to completely cure the HIV patients. So what we want is a molecular sentinel that can detect the hidden viral genome and delete them from our DNA. And so our idea is to program Cas3 and send those Cas3 pacmans to degrade the circular RNA viral genome into pieces. And for integrated DNA, we can program 2 of those pacmans in a head-to-head fashion to delete the viral DNA from our DNA. Another thought is to apply CRISPR-Cas3 for anti-cancer applications. So cancer is the result of spontaneous mutation in our own cells. And so in many cases, the driver event has been well defined. For example, a reciprocal translocation of chromosome arms has been shown to cause cancer in many cases. And this is because this event leads to very predictable gene fusion event, and the product of that gene fusion essentially gave the mutant cells unfair growth advantage, and they became cancer. So one way to cure those cancer is basically to program the CRISPR-Cas3 pacman specifically against the breakpoint sequence and send off the Cas3 to inactivate the fusion gene, and that will for sure halt the growth of the cancer cells. So as you can see, we have came a long way from mechanistic understanding to the therapeutic usage of Cas3, and we hope that we'll mature the tool and bring it to fruition, and we hope that this will benefit the greater mankind.
One of the main worries I hear people express about the new gene editing technologies is that they'll put us on a slippery slope towards a future dystopia in which a genetic arms race puts pressure on parents to design babies to be not just free of serious diseases and disabilities, but smarter, more athletic, more beautiful, in short, better than well. This Mother Jones article asks, is embryonic gene editing research a slippery slope to designer babies? And similar headlines are very easy to find. Slippery slope arguments are, in fact, ubiquitous in debates from gay marriage to gun control. And I see it in my students. So when I ask my students what their instincts are about hot-button moral issues, the slippery slope argument is one of the first things they'll reach for. So given the work we ask these arguments to do for us, it's worth subjecting them to some scrutiny. This is a graphic illustration of the slippery slope worry. So the vertical axis there measures how good or bad our circumstances are, and the circumstances are mapped by that red curve. So the higher up that curve climbs, the better we're doing. The further down it slips, the worse off we are. So we're hanging out here in the status quo, and that's a world in which human gene editing is still very much in an experimental phase. It's not something the general public has much access to. Now, it looks like if we start climbing up that curve to a world where gene editing technologies are widely available for the treatment and prevention of serious diseases like sickle cell disease, that's an improvement in our circumstances, right? A move up to that peak. It looks really good. But proponents of slippery slope worries will say, as attractive as that peak is, once we unleash that technology, there's not anything that's going to keep us from sliding all the way down that slope into the valley below. And that's the world of designer babies. Now, the first thing I want to point out about this picture is that how effective that argument is, how worried we should really be about that slide into the world of designer babies, will depend a lot on the overall shape of that red curve. So the way I've drawn it here, the status quo is pretty good, right? The world in which access to these gene editing technologies is highly limited, where we haven't yet fully embraced the technology, is a world that's pretty high up that vertical axis. We're doing pretty well in that world. But if you have sickle cell disease, you might think I've gotten the shape of that curve all wrong. The status quo is not okay. Things are very bad right now, and we may as well run that risk of sliding into the second valley if running that risk is the only thing that will give us the opportunity to climb out of the valley we currently find ourselves in. Either way, why think we'll slide off that peak at all? Why can't we just stand firm at the top of the peak? So proponents of slippery slope arguments will argue that unless we can find some sharp cutoff point between the kinds of conditions that we think justify intervention with the new technologies and the kinds of conditions that don't, inevitably accepting those interventions in some cases will lead us to accepting them in others, and then in yet more until we end up at the bottom of the slope. So use the technology to prevent or treat cancer? Sure. Sickle cell disease? Yes. Well, what about high cholesterol? How about asthma? How about unusually short stature? Well, once we're using these technologies to address unusually short stature, why not make people a little bit taller, and so on? Now, that kind of reasoning actually relies on a fallacy, sometimes called the continuum fallacy or the line drawing fallacy. We don't actually need to deny the existence of a complicated gray area in the middle in order to insist that there are certain conditions on one end of the spectrum that clearly justify interventions with new technologies, and other conditions or other situations on the other end of the spectrum that clearly don't justify such interventions. All we need is a principled account of why we should use the technologies to address, say, cancer or sickle cell disease, and why we should not use them to make people taller or better looking or smarter than average. Whether or not that principle will pump out a clear answer for some of the hard cases in the murky middle, like asthma or unusually short stature. Okay, so now let's think a little bit more carefully about that metaphor of the slippery slope. Certainly, it can be hard to stand firm at the top of the slippery slope, and that's partly because gravity accelerates. So take even a small step down a slippery slope, and you start building momentum, and it actually becomes harder and harder to stop. But it's not clear what could be playing that role of the accelerant in the cases that we're thinking about here. Now, it's likely that if we accept one conclusion, say that we should use gene editing technologies to treat or prevent cancer or sickle cell disease, we're more likely to accept the next conclusion, say that we should use those technologies to prevent high cholesterol. But it doesn't follow from that we're likely to end up all the way at the bottom of the slope embracing designer babies, much less that it's inevitable that we'll end up down at the bottom of the slope. A better metaphor might be that of a chain of dominoes. So certainly once you knock over that first domino, the second one is very likely to fall over, and probably quite a few dominoes will fall over. But as anyone who's ever played with dominoes knows, it's actually really hard to get that last domino in the chain to fall over. And that's so in the absence of something like a gain in momentum, the domino effect sort of tends to peter out. And that's particularly true in cases where we don't want to knock over that last domino in the chain. We don't want to end up in the world of designer babies. Again, maybe we can prevent that just by identifying a principle that can help us help us explain cases where we do want to intervene with new technologies and cases where we don't. Now, what a principle like that might look like is a topic I'll have to save for the discussion.
So we'll start with a question for Along. You talked about the possibility of using CRISPR Cas3 to delete viral DNA that has inserted itself into human DNA. Could you say a bit more about just how that works? Like if a person's whole body, all the cells have been infected with the virus, you can't, I guess, do gene editing on each cell one by one, right? So how does it work?
Well, so to delete the DNA, delete the viruses from integrated, to delete the integrated viral DNA is going to be more tricky. So we'll have to target two sites, basically at the end of the viral genome, and then send the tool in a head-to-head fashion, kind of send them in a bidirectional fashion to erase the DNA in the middle. And then we rely on the host repair system to then patch it up. So, it really depends on, so you asked the question about whether we can deliver it to every cells in the body. In many cases, we don't have to do that. If we know enough about the the biology of the virus, for example, in HIV, in the case of HIV, we only need to deliver it into to the T cells. And basically all the latent HIV viruses are residing in the T cells. So we only need to target certain kind of cells. So in most cases, we don't have to deliver it to every cells.
I see. And so what kind of time scale do you envision before CRISPR Cas3 and other CRISPR technologies can actually enter therapeutic use? Are we talking years or decades, or what do you think?
Right. Well, I guess it still takes years at least to mature the technology. So when I talk to clinicians, they immediately get the impact, significance, and they're super excited. But we still have to do our homework. We still have to make sure it's safe. And there are a lot of technologies that we still need to be developed to make this tool very efficient at doing its job. So we'll have to do the routines, starting from cell cultures, migrating to small animal, big animal, before we can start the clinical trials.
So thank you. So Julia, some people have probably heard about the CRISPR babies a few years ago in China, whose genomes were manipulated when they were embryos. And that was far sooner than anyone thought this would happen. So evidently, it's time to be developing regulations and ethics guidelines for this type of research. Can you talk about whether regulations are being developed and what role, if any, philosophers are taking in the process?
Yeah, absolutely. They're definitely under development, and philosophers are very much a part of that discussion. In fact, I think a major summit focusing on just that question, how we can regulate the use of this technology worldwide, is just wrapping up today in London. And that included philosophers alongside scientists and sociologists and legal experts and representatives of different fields, because really a lot of these different areas of thought are intersecting when it comes to these questions. We really need expertise in all of these different areas in order to figure out how to regulate this. What kind of enforcement mechanisms are needed to regulate something like this internationally, what the scientific possibilities are, what the scientific risks are, whether this will increase social inequality, and then of course the moral questions about what would justify these interventions and what wouldn't, what are some of the moral objections to these kinds of interventions, and so on. So really it is a topic that lies at the intersection of all these different fields and really needs the cooperation of people who think about all these different sorts of questions.
Mm-hmm. You talked about the continuum fallacy, this tendency to deny the existence of a gray area in between clear-cut cases. So I never knew that fallacy had a name, but it strikes me as very common. Thinking of, for example, the debate around deplatforming or cancel culture. Does the philosophical analysis of the fallacy in the case of gene editing kind of also carry over to other instances, or is each circumstance kind of different?
Yeah, absolutely. I think it definitely carries over. And one reason I chose to sort of focus my comments on the slippery slope argument is precisely because it's so ubiquitous, not just in debates about gene editing, but in all sorts of moral and political debates. You brought up cancel culture, abortion, lots of different, gay marriage. It comes up all over the place, and a lot of the same issues are raised in these different areas. Though, of course, different issues are raised as well. That's not to say that slippery slope arguments that appeal to the danger of this sort of fuzzy middle are always fallacious, or that they're all equally fallacious. It's more that I think they're often sort of lazy. I think people will tend to say, well, that puts us on a slippery slope, and think that sort of settles the matter. Whereas I think it doesn't settle the matter. The difficulty of drawing a sharp line doesn't prevent us from coming up with a kind of principled account of why we should be happy with some outcomes and worried about other outcomes. But of course, it also doesn't absolve us of the need to come up with that principled account. That's still something that we have to do. And what that will look like, of course, and whether we can come up with such an account will vary from case to case.
Mm-hmm. Thank you. Now on to our next segment.
So I'm a particle physicist, and what we particle physicists like to do is we like to take things apart and find their smallest constituents. So we like to go to the smallest matter and pull it apart until we can find nothing that's indivisible anymore. So everybody knows about atoms, and atoms are made of nuclei and electrons, and those nuclei in turn are made of neutrons and protons, and those in turn are made up of quarks. So what we're trying to do is we're trying to study the quarks and see what they're made of, and also try and see if there are other particles that mediate the forces between the quarks. Most famously, the scientists, particle physicists, including teams that people at Cornell, myself included, are on, have discovered is the Higgs boson. So to give you a sense of scale, an atom is about 1/10 billionth of a meter in size. Neutrons and protons are about 1 quintillionth of a meter in size. And quarks, what we're looking at right now, are 1 billionth of a meter in size. So in order to set a scale for that, what I like to do is I like to think of, instead of going from 1 meter down to the size of a quark, I like to go from that 1 meter upwards in the same amount. So as if I was examining at the same different scale. And in order to do that, you go from 1 meter to about 172 light years, so about the size of a globular cluster. So that gives you a feeling for the immense size, how close we are looking at the very smallest scales. So what kind of instrument do we use to do this kind of science? Well, we use particle colliders. In particular, the Cornell scientists work at the CERN Large Hadron Collider, which is shown here in this image. It's located outside of Geneva, Switzerland. And to give you a sense of scale, right here is a picture of the Geneva airport with 2 daily flights to Washington and to Newark. The collider itself is 17 kilometers long, and it's shown here. It straddles the French-Swiss countryside, which you can see in the dotted line in this image. The lab itself is located on the side, and also it straddles the French-Swiss countryside, so I can have lunch in France and walk over to Switzerland to do some science. There are 2 main experiments at the Large Hadron Collider. What we do there is we collide beams of protons, counter-rotating beams of protons at 2 locations, at the ATLAS detector and the CMS detector. The CMS detector is the one that Cornell is participating in, and a bunch of us work there and have been working there in the French countryside for doing really great science. So what does this detector actually look like? Well, here's a cartoon, and the way to think about this cartoon here is at the very center of the detector is where the protons are made to collide. So those proton beams, our detector is like a camera, and it's in some ways very similar to the camera in our cell phones, and in other ways it's very different. Rather than being able to take a couple of pictures a second, this camera takes pictures in 3 dimensions and can take 40 million of them in a second. And so it's an immensely powerful camera. It's the size of a 6-story building, and it weighs as much as more than 3747. So it's a gigantic device. Here's some pictures of the device itself. The horizontal tube you see there is where the protons come in. This is it during its construction, where it was gently lowered into a cave about 100 meters below the French countryside. And in parts, the detector can be strangely beautiful. So this is looking at the very innermost part where the beams are made to collide. During the construction, there was a lot of concerns that we would destroy the universe with our scientific experiments. So we put together this CMS abort switch to try and say that if we ever were about on the verge of destroying the universe, we would turn this off and prevent that from happening, just letting off a bunch of steam. So what's shown right here is an image, a cartoon of what such a collision might actually look like. So what you're looking at is the innermost center of the detector, and soon you'll see two yellow dots coming in and representing the two counter-rotating beams, and they collide. And this is one of the pictures, what it looks like, a three-dimensional view of all the different particles coming out of the collision, and where we can extract what happened when those two protons hit each other. So one of the problems with our cameras is that we can take a lot of pictures, but we can't afford to store them. Just like in Google Storage, maybe Google Photos, maybe you can only store so many pictures. We can only save about, of the 40 million pictures that we take, we can only save about 10,000. So we have to decide very quickly, based with some special calculations, whether a picture is worth saving or not. So in this particular image, you're seeing a specialized computer built at Cornell that allows you to suck in the immense amount of data that the LHC generates and do some very quick calculations to decide whether a data is to be kept or to be rejected. The analog of how much data this device can absorb is it can absorb the equivalent of about 35 4K movies per second. So it's an immense amount of throughput, and it's a very specialized and very cool technology that we're using to do the science that we do. As a result of all of this is our standard model, the standard model of particle physics. And what you're seeing here are the quarks and leptons and the force carriers and the Higgs boson that make up all the material that we know about in the universe around us. So we have a very complete picture. We know almost everything about the material that makes up this table, this chair, this room that I'm sitting in. And what you're seeing right here is an image of the data that we collected where we finalized the picture we did that made the discovery of the Higgs boson. So what's shown in blue is the data coming in from all the other physics that we knew about. And then in red, what's starting to peek out in this image is the discovery of the Higgs boson. So this is data collected over a period of a couple of years and culminating in 2012 in the discovery of the Higgs boson and that raging peak that's appearing there in the plot there. So that was a very exciting time for us in the LHC when we made that discovery. Since then, we have continued with our understanding of the world around us and of all the particles, but we're by no means done. Cosmology tells us that the universe around us is actually made up of about 73% dark energy and about 23% dark matter, and that the stuff that I was just describing, the thing that's all around us, the energy of it, is really only about 5% of the matter content of the universe. So we know almost everything about almost nothing. So that's what the goal is of particle physics in the future, is to try to learn more about the rest of the energy content of the universe, and we're really excited about it.
In cosmology, we seek to understand the universe as a whole. What does it contain? How did it begin? How will it end? And why is it the way it is? In the 21st century, cosmology is an experimental science. We have telescopes all across the Earth and in space that have given us a beautifully clear picture of what's out there. But seeing more, measuring more, has not answered all our theoretical questions. In some ways, it has only sharpened them. Perhaps the most important question in cosmology today is, why is the universe so large? How large is it? Well, it's quite possibly infinite. But the part that we can see is finite, but vast, almost 100 billion light years across. And it's profoundly empty, mostly void, just barely dusted with stars. The problem is that quantum mechanics, our exquisitely tested theory of the very small, does not allow the universe to be completely empty. Quantum mechanics fills voids. It fills voids with particles that appear and disappear. And Einstein taught us that particles curve space. Matter curves space. And so the particles that quantum mechanics makes in otherwise empty space bend the universe and make it expand or collapse. How much do they bend it? Well, as theoretical cosmologists, we're concerned with fundamental mathematical equations, quantum mechanical equations, and part of our work is to find solutions of those equations that describe universes. Almost every solution that we find is a universe not much larger than the smallest particles it contains. A universe in which the smallest particle is an electron, it will be not much bigger than an electron. There's no space to live in a universe the size of an electron, and there's no time to evolve. But here we are in a gigantic ancient universe. And the matter around us is made of very tiny pieces. Quarks and electrons for sure. But what's more, 100 years of struggling to understand how gravity and quantum mechanics fit together has led us to think, not to know as an experimental fact, but to accept as a theoretical one, that matter and space are made of outrageously tiny pieces, strings. A string is 1 trillion times smaller than an electron, and quantum mechanics seems to say that the universe should be no larger than a string. So we face an intense conflict between our theories of the very small, which demand that the whole universe should be microscopic, and our everyday experience of an external world. So why is there a macroscopic universe at all? How did this happen? We don't know the answer today, but we do have a hint. When we dig at the foundations of physics, we find mathematical structures. String theory, it turns out, is a theory of numbers. Every universe that comes out of string theory is completely specified by a finite list of ordinary numbers. These numbers are like a code. Put in the code and out comes a universe. And almost every code that we put in, we get out a universe no bigger than a string. But my research group at Cornell has found a new class of codes that give universes larger than our own from the equations of string theory. Here's one such code. It's small enough to fit on a t-shirt. This is the complete mathematical DNA of a universe more than 100 billion light years across, and all made of microscopic strings. The universes we found are not completely realistic. For one thing, they don't contain the particles needed for life. But they do answer the question, how can a quantum mechanical world be much, much larger than the particles that it contains? And perhaps by following this line of work, we'll one day understand how our own universe came to be.
Liam, I'll start with a question for you. Could you explain in more depth why quantum mechanics suggests that the universe should be the size of the smallest thing in it, the size of a particle or a string?
Sure, yeah. So Einstein taught us that a region of space with high energy density will be highly curved. And so we just need to know, what does quantum mechanics predict for the energy density of empty space? So if I take a jar and I look inside it, if I try to empty it out, I'll see electrons appearing. Well, the question is, how many? And there's a principle of quantum mechanics that says that everything not forbidden is compulsory. So electrons won't just appear 1 or 2 per jar. They'll pack into every space they possibly can, shoulder to shoulder. But then what about smaller particles? And so for this, we have to remember that in the quantum realm, small things are high energy things. An ultraviolet photon and a microwave photon are made of the same field, but the ultraviolet photon has smaller wavelength and a lot more energy. So a smaller, heavier particle, like say a top quark, will pack into every gap it can find in the jar, say. And a jar of top quarks weighs a lot more than a jar of electrons. And so whatever particle in the theory is smallest and heaviest is going to control the answer.
So tell us a bit more about how you go about looking for the right code, like the right set of numbers governing the strings that will produce a big universe like the one we live in.
Each of those codes corresponds to a 6-dimensional geometry, and so we needed to learn how to list and then search through those sorts of geometries. And that's a well-defined math problem, but early estimates suggested that even if you ran it on a supercomputer, it would take more than the age of the universe to find even one solution. So we thought for a while, we found much better algorithms, designer algorithms that directly make what we want. And with those, we can now find solutions in milliseconds on a laptop. But then to find the solutions that correspond to large universes, we used the power of exponential growth. We found geometries whose codes have the size of the universe be an exponential in the numbers appearing in the code. So one example, we found a geometry whose code contains the numbers 126 and 29. And that describes a universe that's about 126 to the 29th power times larger than a string. And that's as big as the observed universe.
Cool. So Peter, can you talk about why smashing particles together at the Large Hadron Collider is a good way of searching for new elementary particles and new information about the universe?
Sure. So in order to do, what we do there is we take advantage of the one formula in physics that everybody knows, which is E equals mc squared. So E in this case is energy, and mc squared is mass times the speed of light squared. So if you ignore the speed of light squared for a moment, that's just a constant. What it says is that the energy, you can trade energy for mass. And so in this case, what we do is we accelerate the protons as fast as they can go, That gives them a lot of energy. And with that, we can create massive particles that maybe haven't been seen yet since the very start of the universe, sort of a 10 billionth of a second after the Big Bang. So that trade-off is what we take advantage of at that Large Hadron Collider. To get you a feeling for how fast the protons go that we use, we accelerate them to a point where the difference between them and the speed of light is sort of about the speed of a middling runner, sort of like 6 miles an hour or so. And we try and by making them go faster and faster, we can create heavier and heavier particles via that E equals mc squared relationship.
Great. And the Large Hadron Collider is starting up soon again after hiatus. Will you be going to Geneva? And if so, what do you actually do there?
Yeah, so I'd love to say that I take like a special bag of my own protons and go and collide them and then come back and collect the results. I do go there a lot, but I don't go there to actually run the experiment. The experiment, at CERN is where the World Wide Web was founded. And so the idea, we have a worldwide collaboration, we can do almost everything remotely. But nonetheless, what we find, and I think we all know this in this era of Zoom, is that those interpersonal relationships are really important. And so we go there to meet, to talk, to hash out new ideas, to visit with my graduate students and do all those things. Because even in this digital age where we're all able to connect anytime via social media or via Zoom, those interpersonal connections, that face-to-face is where I think the real creativity comes from and where you can really have dynamic and new ideas. And so that's the main reason we go there, paradoxically. It's not to do science, it's to be social and talk about science.
Sounds fun, and good luck with the run of the collider.
Thank you.
And so now we'll have a polling question before our special intermission. Question is, which technology would you prefer to see realized in your lifetime? A nanorobot to fix your health problems, or a CRISPR gene editor? So please select between I would prefer a nanorobot or I would prefer a CRISPR gene editor, and I'll read out the results of the poll. Oh, scan the QR code on your screen to join the poll. All right, the results are coming in. Oh, okay, so it started out that nanorobots were ahead, and then CRISPR made a comeback, and okay. Let's see, wait for a few more seconds. All right, so we have, it's still varying a little bit, but basically about 60%, high 50% think a nanorobot would be more exciting, and then the remainder, so slightly less than half, think that CRISPR would be better. All right, and now for our intermission.
Hi there, my name is Michael Reynolds. I'm a postdoctoral researcher at Cornell University, and I collaborate with Itai on the project on nanorobotics. So what I want to do today is show you some cool macroscopic demos, things at the big scale, to give you an understanding of the things that we do at the very small scale. One of the things that we can do with these super thin materials that Itai talked to you about during his talk today is fold them into origami shapes. So basically using origami as a way to think about making things that fold by themselves, things that are robots. And so to demonstrate this, one of the things that we folded was a nanorobotic origami bird. And so I want to show you how to fold a macroscopic origami bird today in paper, just like the one that we folded nanorobotically at the micron scale. Let me talk you through the fold pattern to do that. So you'll start off with a square piece of paper that you should have with you, and you'll fold a diagonal fold, one corner to the other one. Great. Once you've made that fold, you should have something that looks like a triangle. And now what you can do is take the flaps on either side of the triangle and fold them down to the side, like so. So you should have a shape that looks like this. Once you get this shape, the next thing that we'll do is fold kind of the long part of it over. And this is what's going to become the neck of our origami bird. Fold it like that. And then we'll fold it back the other way, just to kind of strengthen, make that a stronger crease. And then go back to the shape that we had before, but now we have a nice crease here, right there. The next thing that you can do, if you open up on one side one of these flaps, you should be able to push that in, kind of reverse the fold, make the neck like that. And then we'll do the same thing on the other side. Open it up on the other side, push that in. Like so. And so now we can open it back up a bit. You should have a shape that looks like this, where you'll have a tall part here, a mountain fold we call that. And the thing that we want to do next is flip the direction of this fold after the vertex. So we'll push that through like that. And then do the same thing for these two folds here. And if you do that right, what you should have is something that folds up like so to give the neck of your origami bird. And the next thing that we want to do for this origami bird is give it a beak. So we'll fold a similar fold like this. And then back the other way. And then you can do the same sort of thing that you did before, where you open it up a bit. And sorry, guys, give me 2 seconds. And what we're going to do is reverse the direction of this fold here so that it becomes a mountain now, and these two become valleys. And that should give us the beak of our origami bird. And so when you're all done, it should look like this. And this is the exact same fold pattern that we do at the nanoscale, but now reproduced at the macro scale. So what it shows is that we can take inspiration from origami to fold all sorts of shapes at the nanoscale with these ultra-thin sheets. But now the only problem is that when you're folding at the nanoscale, you obviously can't just do it by hand. So you have to have something called an actuator, something that will fold by itself. And so the other thing that you should have is a little toy example of an actuator. It's in this little packet maybe, and this one happens to be in the shape of a fish. But if I put this fish on my hand, what it will do is start to bend up all by itself. And it folds like this because this fish is sensitive to water. Basically, if moisture gets into the plastic that makes this thing, it makes it swell on one side. And so because my hand has a lot of moisture on it, it will fold away from my hand. Now the actuators that we use at the nanoscale, they aren't sensitive to moisture, but they're actually sensitive to voltage. Basically, if you apply an electric signal to them, you can get them to bend. And so that's what allows us to make them into robots. And so I have one more toy that I want to share with you today, and it might be a familiar toy to some of you. It's Legos. And one of the things that I got to do, in addition to making robots at the nanoscale, was to make some macro scale Lego models of the exact same sort of robots. And so just like our nanoscale robots that Itai showed you a bit ago, these robots have a brain, this big circuit component right here, and then legs with hinges that can fold. So once this guy is turned on, if you tell it to start, Then the brain will send electrical signals to the legs and allow it to walk off all by itself. And so this sort of walking robot will save it from falling off the table. Is the exact same sort of design that we're able to build at the nanoscale using these tiny actuators and also our onboard electronic brains. Thank you.
Thank you, Michael. Hope everyone's bird folding went better than mine did. And thank you to everyone who entered our Envisioning the Future contest. These were some great entries, and we appreciate all the thought that went into them. I'm delighted to announce that the winner of our elementary school category is Luca Schwartz. Here's Luca's winning essay. Luca writes, "Yes, I believe that tiny technology can and will change our lives. Microscopic technology such as robots can carry a huge amount of information and share that huge amount of information with other microscopic technologies at super fast speeds. Robots affect our everyday lives, even if we do not notice. They are more powerful and smart than us humans think. Some people say that robots will take over the world someday. This shows that robots are very powerful, sometimes more powerful than human beings. We travel using cars, airplanes, and other transportation vehicles. Maybe someday, scientists will figure out a way to use tiny electronics and create something else more efficient, newer, and environmentally friendly that can take humans and maybe even other animals places." In the high school category, there are two winners. One visual arts submission by Avalon Golden, whose image depicts how nanotechnology will help create a carbon-free atmosphere. Beautiful. And the winning essay is by Sophia Schumacher. Sophia wrote the following. "Microscopic entities have been revolutionizing the fields encompassing the applied research sciences for decades, with nanomaterials emerging at the forefront of much technological innovation. Although they have been utilized for applications ranging from genetic vectors to water filtration, I believe that these machines truly have an important role to play in the future of the biomedical treatment of degenerative diseases, a class of conditions which impair millions across the globe. Biocompatible microscopic robots could be engineered to biosense for regions of these diseases through detection of certain stress signals, and then consequently bind to these regions. Afterwards, internal treatment delivery to these regions could be triggered through this binding, whether it be reconstruction of diminished sites using nanoscale tissue scaffolding, or release of certain chemicals to trigger regenerative signaling pathways. Through such methods, not only is the vast versatility and precision of these microscopic robots discovered, but also its effectiveness in treating some of the most detrimental disorders impacting our current world, including ALS, arthritis, osteoporosis, etc. And finally, the winner of our adult category is Vin Churang. Vin's essay reads, "Our exploration of the very, very small has guaranteed us one thing, that we are no longer afraid of the very, very small. In the past, we let nature handle all of the small, hoping that evolution over millions of years would be able to perfect itself. Unfortunately, we don't have the time to wait, as problems challenging human health in the world are forcing an immediate response. Luckily, the scientists of today are helping us curate this reply. Advances in CRISPR herald a world where we are able to compete with nature on an even footing. Genetic diseases will become a thing of the past, along with world hunger as we develop climate-resilient and disease-resistant crops. Robots on the nanoscale level will aid these efforts, giving us control of the wild, wild microscopic landscape populated by DNA and proteins. By getting rid of health and food problems that seemed hopeless in the past, we welcome a world where everyone is given an equal opportunity at life. While our future seems to be focused on the very, very small, I think it's also safe to say that it is also very, very bright." Congratulations to all our winners. Your essays and artwork will be posted on the College of Arts and Sciences website, and you'll receive a gift certificate to Buffalo Street Books in Ithaca. And thank you again to everyone who entered. Now for our next segment.
I'm a chemist, and I also am interested in other things. A few years ago, I saw an exhibition of images of the nanoworld. Here are two of them, very typical of what you have seen. At left is the gold tip of a scanning tunneling microscope. At right, a diffraction pattern in false colors from a silicon crystal. These are images. They convey information to the scientists studying. For instance, I didn't know that the tip was so rough. I thought of it as being very smooth. But they also have some significance as images, and that is what I want to explore with you. The moment I saw those images, in fact, I thought of a movie I had seen when I was younger called Blow Up by Michelangelo Antonioni. And that movie was of a photographer who was otherworldly in various ways. He took some images in a garden of a man and a woman, and when he blew them up in his studio and kept blowing them up, he saw not only the man and the woman, but also what looked to be a trace of a murder. How real was that, what he saw, as a result of blowing up the image? That's very interesting. How real are the images that you see? Some of them look quite real. For instance, the image at upper left looks just like a Manna Neapolitan. That's a little chocolate wafer that I like, made in Austria, that I recently crunched into. The one next to it, in black and white, and also the one below, they look a little bit science fiction, like otherworldly. I'll come back to that. They look a little bit not quite real. But what is real? I want to show you some apples and fruit made by Paul Cézanne. The paintings at the Metropolitan, the fruit at the middle at the top is probably a persimmon. There are no black circles around real apples. These apples, which are more real than real, are representations as much as the scientific images that you see, which are of electrons passing through some sort of object and then impacting and giving a signal. These are all representations of reality. What's interesting to me about them is that the scientists who show these to you, to me, are making artistic choices. They don't think they are, but they are, in the process of showing them. So for instance, here is a bunch of nano dots. Now, the scientists could have chosen them to you, could have chosen to show them to you in a square array shot head on, like a bunch of soldiers marching. But how much more interesting is what he did, thinking simply artistically about the form of the presentation, that it's at an angle, that it's cut off. All of this makes this much more interesting and therefore draws you in to examine it closely for the scientific content that's in it. The choices that are made are subtle sometimes. At left are some tin oxide nanowires. The thickest of these is thinner than a hair. They are in focus, they are out of focus, they are darker or lighter. The choices that are being made in this presentation are not that different from the choices in a classical Chinese painting, such as you would see on the 5th floor of our Johnson Museum. There is one of these paintings at right with a woodcutter in front, and there is a middle ground of a stairway leading up, and then there is a background of those wonderful mountains in Guilin province in China, which are real. These are artistic choices that are being made. One interesting question one could ask is, of these images, of these types of images, which will persist 100 years from now, which will enter the vocabulary of artistic representations of the future. I think these images, which look otherworldly, in some way unreal, are more likely to do that than the straight-on realistic images that you see, just because we don't know quite what to make them, and that's what makes it interesting. I want to end with this image here. It's nothing complicated. It's a glass surface that's been bombarded with argon ions to clean it up. Maybe it's multiplied 100,000 times. But when I see this image, I think of sand dunes. I think of the recent filming of Frank Herbert's novel Dune by Villeneuve, a beautiful film. And I think of sand dunes I have seen in the Sahel. I think of every other image of dunes that come to mind, and I also think of that glass. I bring together the art and the science, and this is what I like.
We live in a time in which all the planet's ecosystems have been modified by human activity. The land where we walk, the air we breathe, the water we drink, contain particles that are the product of human actions. Carbon dioxide and BPA are invisible to the human eye but can have an impact in our health or in the environment. There has never been such a great distance between the reality of a place and its appearance. The air can carry pollutant nanoparticles that produce cancer and still look clear. The ocean may look pristine but be filled with microplastics. Speculative fiction is a narrative mode that includes science fiction, horror, and fantastic literature, and is very well prepared to talk about invisible beings and threats. Writers have imagined tiny creatures, microscopic kingdoms, and little spheres that contain the universe. In Latin America, in recent years, there have been books written in the speculative mode that deal with dangerous and invisible particles. One of them is Samantha Schweblin's Fever Dream, and the other one is Veronica Gerber's The Company. I became interested in the issue of nuclear energy because it's part of the discussion about the way in which we envision our future. The climate crisis has shown us that we cannot keep depending on fossil fuels and we must move to other types of energy. Nuclear energy is a low-carbon type of energy that is based on the very small atoms colliding with each other. However, it poses risks. Radioactive waste can stay in the environment and contaminated for hundreds of years. In Latin America, there are 7 nuclear plants, and Bolivia is planning to build a new one. There are benefits to the project. For instance, the Bolivian government wants to use the plant to find treatment for cancer. But on the other hand, there are problematic aspects to the project, like the fact that the nuclear plant will be built close to the indigenous city of El Alto, where many people are poor. In order to convince the population about the benefits of the nuclear plant, the Bolivian government created an animated superhero called Atomito, which translates as Little Atom, a cheerful boy who explains how the plant will work. The happy face of Atomito and the possibility of having complications with the nuclear plant inspired me to write a book of short stories written in the speculative mode that deals with the issue of toxic waste and with the problematic fact that it is usually the poor and indigenous communities, the ones who receive toxic waste in their lands. I was also inspired by the radiological accident in Goiânia, Brazil in 1987, in which two scrap collectors entered an abandoned building and dismantled medical equipment that treated cancer, releasing radioactive particles. Science has been able to create wonderful things and very small things like microchips, but is also responsible for dangerous particles. The distance between the harmless appearance of an object or a place and its secret and sometimes threatening reality is a feature of speculative fiction and one that has become increasingly relevant to talk about the present.
Solace. A hummingbird hovers in air between droplets of rain, showers in a single stream. The storm, a wholeness broken into sparkling strands, into globules cracked like clear casks over the bird's jewel-toned crown, splashes silver. Delight wings. Go, little rock star, 40 beats per second. Tick-tock, but stillness. Suspense. A hummingbird breaks the day. Suspense sustains. Slow me then. In rarefaction, you moved into rain between black and green where lift resides. The life reorient, dwelling come to singing, buzzing. A crow knows what it knows. We are made giddy, delayed. A shared vibration holds us up, black, greening every span of shade to determine the shape of the body's inclination, the density of the air, folded like a note, passed between two huddled girls, laughter, ruby throats. I write a lot from science, and one of my obsessions is roaming fragments, and another is thinking about identity and particularly about gene expression. I wrote a book called Open Interval, in which I did a meditation on my own name, using the RR Lyrae stars with which I share a name, but also thinking about the body and elements of my identity that may not be visible to people, one of which is that I have the sickle cell trait. And I think a lot about that mutation, how it might have happened, what it looks like when you focus in on something like that in the body. I want to reflect that kind of thing in my poems when I'm writing, how the poem might come from a poetic lineage, for example, of other poets who are thinking about science and write from that and teach me how to write and read from science. So someone like June Jordan or Lucille Clifton, who wrote the Book of Light, and based on her name, Lucille, thinking about how light breaks things apart, for example. So in a poem like this, I want to make visible the fragments that come together to make the poem, both in terms of breaking up the sentences and including the punctuation that I use that I call bonds in the sentences to see how fragments have come together to make the wholeness of the poem. But even thinking about the structure of the poem itself, this poem is a formal poem called a haibun. A haibun is made up of a prose journal description and a haiku. So the way that those two forms work together and are held together in the poem is one of the ways that I reflect that, thinking about roaming fragments. When I think about poetic lineage, you can find things like the italicized lines, the life reorient, and every span of shade are taken from a long poem called In Memoriam by Tennyson. And Tennyson in that poem is thinking himself about, in part, science and faith and the tensions between and how they work. And so that's one of the things that I wanted to share, but also to think about how the poem is in part thinking about lift, and the equation for the lift equation is hidden, or maybe not so hidden, depending on who's the reader. If a scientist is reading the poem, maybe it's quite visible. But the lift equation, pieces of it are also included in the poem so that the poem is revealing its own materials as you read it down the page.
Very interesting. So I'll start with a question for Roald. Some of your comments made me think about how in the late 1800s, physicists were debating the existence of atoms, and it took a long time for everyone to be convinced. So we only had indirect evidence. And to be convinced, we really need to directly see something. We need an image. I was wondering if you could talk about the scanning tunneling microscope that you showed a picture of, and talk about the impact that that microscope has had on our understanding of nature.
I'm sorry to say very little. Here's the reason. In the beginning, those pictures that came out of IBM laboratories, a commercial laboratory, they appeared in ads. The ads had a picture of Democritus, a white guy with a beard, and right next to it, it said, "Now for the first time, after 2,500 years of trying, you can see atoms." I nearly went through the ceiling. That was a travesty of all the work that chemists had done for 200 years, where we had gotten good evidence without seeing. And that's very interesting, isn't it? Now, knowing without seeing, the scanning tunneling microscope helped a lot. And we have seen some things, but one has to be very sure that one is seeing what one thinks one is seeing. And that's a real job.
All right. So you also mentioned that scientists make artistic choices in the images that they show people. I'm wondering what you think motivates their choices. Are they aesthetic, rhetorical? Are they using images to support an argument? And if so, wouldn't that make science kind of more subjective than people tend to assume?
I think the choices are both artistic and rhetorical to make a point. They are artistic, and the scientists would really benefit from an introductory course in studio art to learn something about the relationship of the outside to the center, about where to cut off things, how to display something. Most of them learn it intuitively. As for scientists being subjective, yes, science is a wonderful system for gaining reliable knowledge. I would not say truth. We can talk about that. Based on the ideas and observations, it has to be experiment there, of fallible people using instruments that they always mistrust and that themselves are fallible sometimes. But providing you have an open communication system, it'll come out what the truth is eventually, or what the reliable knowledge is. So the individual scientists are fallible, but the system actually is an incredible social invention.
Thank you, Roald. Liliana, what role do you think that speculative fiction plays in helping society understand its problems and possible solutions?
speculative fiction deals with timescales that are larger than human life, and human life is very short. And for instance, radioactive waste can stay toxic for hundreds of years. And speculative fiction is very good at dealing with different experiences of time. For instance, when it talks about time travel, in other words, it makes us aware of time in a much larger scale. Speculative fiction also helps us stretch the imagination to think about the invisible as something that has a presence and has a real impact in our lives. And finally, speculative fiction has also anticipated many technologies of our time, like cell phones or the internet. And who knows, it may help us imagine solutions to any sort of questions that we might have.
Hope so. And Lyra, could you comment on any similarities that you see between poetry and science? Like personally, I'm struck by how they're both inquisitive, and also how both can be quite cryptic. The sort of languages for talking about the world that not everybody speaks. I don't know if you have thoughts on that.
For me, both poetry and science involve mystery and finding a delight in discovery. A poem may seem cryptic, but there are processes that one might find if one looks closely, and at unzipping an image or articulating an idea, and thinking about how is a poem built, and how does meaning move, and what happens in the gaps. I'm a Black woman poet living in a world that compels me to be interested in melanin, for example, but often fails to imagine or ignores or tries to dictate the ways that I might be interested in it. And so it delights me to think about how looking at a multi-layer melanin-filled platelets in hummingbirds, barbules might translate into the way I structure a haibun, this formal poem. I can play with the science and it transforms the art. Thinking about structural color as part of a coded conversation between two Black girls sharing a moment of delight, I can encrypt a poem with that lifting of spirits that the sight of a ruby-throated hummingbird's iridescence brings. And sometimes the world that I live in, things that lift Black girls' spirits have to be coded, frankly. And that seeming impossibility and necessity of finding a free space in which to laugh makes me really sensitive to where someone might be reading or misreading my body or life as something that needs to be edited, for example. I'm somebody with the sickle cell trait. And so I think about mutation a lot. But who can I speak with about the complexities of my identity and what it means to live and breathe and think in this body, and of the layered histories of my family? And who takes the time to really try and look closely and understand these things? So I hope that the poem delights and invites the inquisitive to ask these kinds of questions, and that the cryptic, pulls people in towards wanting to have those kinds of discovery.
Thank you for sharing your wonderful poem with us. And thank you all. And now for our next segment.
The amazing thing about the universe is that everything you can see here, from the Big Bang up until the stars and galaxies we have today, can be described by four fundamental forces. On one hand, this is amazing because you have all this complexity, but you can describe it so simply. On the other hand, you might wonder what would happen if there were other fundamental laws. Would you have different universes with different discoveries to be made? This is the world of quantum materials research, where each material we study acts like its own universe with its own physical laws and its own discoveries to be made. This is graphene. It's a perfectly atomically thin sheet of carbon atoms, perfectly two-dimensional. It lets us ask questions about the universe, like what would happen if the universe was completely flat instead of the three-dimensional universe we live in. In this case, electrons move around in graphene like they have no mass at all. They just hop from carbon atom to carbon atom effortlessly. This is a superconductor, and it's able to levitate a magnet above it. This is a quantum material where inside the superconductor, light moves as though the photon has mass. Now, in our world, nothing travels faster than light because photons are massless. But quantum materials, this can be different. In this case, photons have mass. Doing fundamental quantum materials research is like being an explorer. Why do we do it? Well, because it's there, because it's exciting. But quantum materials research also drives technology. So this is silicon. Silicon was discovered over 200 years ago, and it took decades of fundamental research to turn it into the information technology and semiconductor industry that we have today, powering everything from the chips inside your cell phone to the solar panels on the James Webb Space Telescope. Superconductors aren't as far along in the technological pipeline as silicon is, but we're still studying them. But all of the wire inside an MRI machine is made of superconductors, and the quantum computers being developed by IBM and Google are also made of superconductors. Fundamental research is never done by one person alone. So here's my team of explorers, and we specialize in building experiments that take materials to their extremes. So we cool them down to temperatures just a few thousandths of a degree above absolute zero. We travel to national labs to put them in magnetic fields that are 1,000,000 times stronger than the Earth's magnetic field. We use those strong fields to really push electrons around and test the fundamental limits of nature. We use ultrasound to peer inside of superconductors and discover new types of superconductivity. We work with groups at Cornell who have powerful microscopes that can look at individual atoms and find where each atom is placed inside a quantum material. Materials have been so important for humanity that we name each age after one. We have the Stone Age, the Bronze Age, the Iron Age, and now we live in the age of silicon. We know that quantum materials are going to power the age of tomorrow, and really the question is, which material will it be?
This is a social phenomena that emerges when many individuals interact according to an agreed upon rule. I am a physicist who studies social phenomena, but at a much, much smaller scale. When you zoom into these people's hands and their phone, there are these electrons. And I study the social phenomena of electrons. Electrons form different communities depending on the social infrastructure, that is the material, and the environment, that is the experimental condition. The material YbCO shown at the top looks dull because in the room temperature condition, the electrons form this chaotic state. We call it bad metal. However, you take the same material and cool it down to minus 300 degrees Fahrenheit, you reach this completely coherent, very consistent state which can carry current without resistance. We call this superconductor. Silicon shown below looks shiny, and it shows that it's a state system where electrons are forming a traffic on the bridge. When the bridge is raised, nothing can pass through. That's an off state. When the bridge is lowered, electrons can flow through. That is on state. The fact that semiconductors can manifest this on and off property at a much smaller scale than vacuum tubes allowed us to scale down the computers from ENIAC to present-day iPhones. However, all of the semiconductor-based technology relies on and off, black and white. So you can wonder, why do we stay with just black and white? Why not go to the full spectrum of colors? Is that possible? It turns out it is possible if you make use of the spin of electron. Spins are a degree of freedom that is in a superposition. It's more like having a full spectrum. There is a phase. Moreover, depending on which angle, which axis did you look at it, it once again looks like it has a full phase. It allows us to encode information in a much more richer way. The foundational experiment in 1920s showed that not only spins can be in a superposition of right or left in this split slit shape, but when you take one of them and look at it from a different axis, once again you find it right or left or up and down. There is this superposition in spin, which gives us the full rainbow. We are a lucky generation because we can now see these spins and implemented into a set of qubits. They can be individually controlled, can be used to be programmed and used for computation. There are many different platforms for implementing the quantum computers. However, this technology is still at infancy. In my research, I try to bridge this nascent technology with more established classical computing so that we can understand what's going on in quantum simulators better, and we can make better use of the quantum simulators to solve problems in the material world, bridging between complex and rich data with theoretical insight.
Matter is made of protons and electrons. You probably know the protons are positively charged and the electrons are negatively charged. We build computers in which we store information using the electrons. Physicists and chemists are trying to build computers based on spin or magnetism. You may not know that these particles are also magnetic. The proton has a weak magnetism. That magnetism can be up or down. And the electron has magnetism too. The magnetism for the electron is much bigger. And it's this magnetism we're trying to use to build the next generation of computers. Now, we don't think of the magnetism of stuff every day, but it's really useful. The proton magnetism is useful for taking pictures of the brain, like in the magnetic resonance imaging machine. That's imaging the proton magnetism. Now, the amazing thing about MRI is that you can build a machine which is meters big and use it to see things that are less than 1/1000th of a meter in size. So on this scale, every tick is a factor of 10. And you see the MRI machine up there bigger than a meter. And yet we can resolve features through the magic of the magnetic resonance phenomenon that are 1/1000th the size of the machine. Now, we'd like to image even smaller things. So here I show on this scale the size of a human hair, which is smaller than what the MRI can see. And then, a factor of 20 or 50 smaller is the size of a cell. 100 times smaller than that, a virus, and then another factor of 100 smaller, the size of an individual molecule. The microscope we're building is aiming to image things at a resolution shown there, smaller than the size of an individual molecule. And the microscope that we've built detects spins using a silicon diving board, which is as long as a human hair is wide, and it's a few thousand atoms thick. At the end of it is this little magnetic tip, which is not a whole lot bigger than an individual virus. What we're measuring in our experiments is the force between this magnetic tip and the spin magnetism in the sample. Now, these forces are very small. An everyday force is 1 Newton. The gravitational force, or the weight, on one apple is roughly 1 Newton. 1,000,000 times smaller than a Newton is a micronewton. Look at all those zeros. 1,000,000 times smaller than that is 1 piconewton. And a piconewton is the force needed to break an individual chemical bond between atoms. Another 1,000,000 times smaller than that is 1 attonewton, and those are the forces that we're measuring in the Cornell Nano MRI experiment. How this experiment works is we take spins and we cool them down to very low temperature, and we place them in a large magnetic field like in the MRI machine. to get the spins oriented. Once the spins are oriented, we bring in our magnetic tipped silicon diving board. We lower the field a little bit, and we get a little extra field from the tip. And then through the magic of the magnetic resonance phenomenon, if we irradiate the sample with microwaves or radio waves, we can flip spins below the tip. Those flip spins speed up the motion of this magnetic tip cantilever, and we can detect this speed up and use it to observe the spins. What are we using this for? Lots of things. First of all, we're using this to image spins in quantum materials to study quantum computing. We're also using this to image the molecules of life. So smaller than a proton, but bigger than a water molecule, are individual proteins. Membrane proteins are particularly interesting because they're the gatekeepers for the cell and otherwise hard to study. And they form complexes with other proteins to make these beautiful molecular machines. How the proteins fit together to form the machines is a big jigsaw puzzle, and it's that jigsaw puzzle we're using our microscope to solve.
Thank you. So I'll start with a question for Yunha. Your research utilizes the spin of electrons. Could you say a bit more about what spin is? It's definitely harder to understand than charge.
Sure. I have eye color, I have hair color, I have skin color, and so on. Those are characteristics of my body. Electrons are much simpler objects because they are fundamental particles, and they have only two things that characterize them. One is the charge, and the other is the spin. Spin is what allows electrons to behave like tiny compass that can point in different directions. When all the electron spins point the same way in a piece of a material, that is a magnet. So all qubits act like isolated electron spins that can be individually controlled and measured instead of all as one gigantic group.
Right, okay. Brad, I love this idea of each material being a universe unto itself. But of course, all materials are actually part of our one universe with its one set of laws. So can you say how materials can act as if they follow different laws?
Yeah, so in physics, we often use what are called effective theories when we look at things at different scales. And I can give you an example, which would be gravity. If you want to build a bridge or you want to fly an airplane or something like this, you'd use Newton's laws of gravity because they're the right laws at that scale. If you wanted to think about how galaxies form or you wanted a very, very precise GPS timing, you need to use Einstein's theory of general relativity. That's the right theory at that scale for gravity. And then if you want to study the center of a black hole or something, we don't have the laws even yet, but you need some form of quantum gravity, some string theory or something like this. So the same thing works in the opposite direction. So those are bigger and more extreme scales. When you go down to the quantum scale inside of materials, electromagnetism behaves very differently. So inside of a metal, you have Ohm's law. Ohm's law isn't something that works out in free space. It's something that happens inside a metal. Inside a superconductor, Maxwell's equations, which are the equations of electromagnetism, get replaced by the London equations. And so these are new effective theories that work inside quantum materials because that's the scale you're studying at that time. So each quantum material ends up with its own emergent laws.
Got it. John, what's the story behind how you invented this silicon diving board? And also, how do you build such a thing?
Yeah, so the tricks we use to make the silicon diving board are the same tricks you use to make silicon circuits. Now, we did not invent the silicon diving board. That was invented for the atomic force microscope, and the kind that we use is very thin, and the process to make that was invented by an engineer at Stanford, Tom Kenny. What makes our diving board special are the very tiny magnets, and to pattern those, you need basically the electron beam,
and you first spin a polymer onto a silicon wafer. You use the electron beam to poke holes into the polymer. You dissolve it away. You then put down cobalt to make the magnets. You then use some more of the electron beam to cut out this sort of silicon chip. And then we use, under the electron microscope, micromanipulators. Basically, by hand, we lift out this chip and use focused ion beam welding and focused ion beam cutting to basically glue it by hand onto one of those silicon cantilevers.
Oh, sounds difficult. Great. So thank you all. And now for a final poll before our audience Q&A. The question is, and again, enter on your own, and I'll read out the results. So the question is, did you know before this event that your smartphone depended on quantum materials to work? Yes or no? Yeah, scan the QR code on your screen to join. I've not done that. All right. So most people did not know that. 60% did not, and 40% did. Yeah. So now it's time to turn to your questions. Some questions have been submitted into the chat already. That's probably all we're going to have time for. So for the first question is for Julia Markolitz. This person asks, what's the problem with designer babies? Specifically, I don't see any consideration of human nature in your argument. Who will stop those with nefarious intent? Or just a different sense of what's okay?
So I think there's a lot going on in that question. So my argument, unfortunately, because of time limitations, didn't actually give me any time to consider what, if anything, is wrong with designer babies. I was more taking a step back and thinking about worries people might have and what needs to be added to those worries to sort of substantiate them. So I think people have different views about, reasonable different views about designer babies. So some philosophers, for example, think that our goal should be to make the lives of whatever children we have as good as they can be. And just as treating certain kinds of diseases or preventing them from inheriting certain kinds of diseases can predictably make their lives better, so can making them taller, so can making them stronger. So can making them more intelligent. Other philosophers have argued that, in the other direction, that we should be not so quick to assume that even removing disease will necessarily make the lives of our future children better, especially when you think about to what extent the kind of hardships involved in the lives of people who have certain kinds of diseases or disabilities can really be attributed to lack of accommodation, social biases, and so on, and that the right response to those kinds of harms is not to try to remove the disease or the disability, but rather to address those social harms. So I think there are arguments to be made either way here. And again, I think this is an area where there's likely going to be a messy middle with clearer cut cases on the edges. There's certain kinds of disease conditions that I think we have very good moral reasons to want to remove. There are other kinds of disease conditions or non-disease traits, which we don't have good moral reasons to want to remove. And then there are going to be hard cases in the middle. And you ask, well, if there's disagreement, who settles that question? Yeah, that's a very good question. I think Natalie asked earlier about what kinds of regulations are in place. And I think they're going about this the right way and bringing together people from all sorts of different disciplines, all sorts of different cultural backgrounds to discuss this together, which I think is the best way to make progress on these sorts of difficult moral questions.
Thank you, Julia. So there's another question for Liam. This person asks, is it possible that dark matter is a fictitious force, simply the effects of dark energy on regular matter?
Yeah, so dark energy and dark matter are different in one important way. We know that dark energy pervades the whole universe almost uniformly. It's stretching the distant galaxies away from us. But dark matter, what we do know about it for sure is that it clumps. It gathers around galaxies. So it's not uniform. It's collected together, it's clustered. And we can even see from the imprint of the Big Bang in cosmic microwave radiation, by looking at the sky with the microwave telescope, you can see patterns there that show two different effects. One of them is a dark energy type effect. You can see the imprint of the fact that 70% of the energy in all the universe is the energy density of empty space uniformly. And most of the remainder is something that's clustered together, that gathers gravitationally rather than staying spread apart. And so for that reason, we know there's really two things going on. Do we know that there isn't any possible description of dark matter by modifying the known forces? We don't know it, but that door is almost closed. We have evidence from so many different angles that the simplest picture is surely that dark matter is some kind of stuff. We just don't know what kind of stuff it is yet.
So what about, I guess, Liam, just to stick with that a little longer, there I think are physicists who don't think that dark matter kind of takes the form that the majority of the community thinks in terms of particles, right? So maybe what this person's getting at is maybe there's some kind of other thing that we're wrong about, not that we're missing these particles, right? And I wonder if you could talk a bit more about that.
Sure. So it's certainly likely that the dark sector is in some way complicated in a way that we might not have envisioned. For some decades before the experiments got better, one was typically told that the dark matter is a particle and its mass is most likely approximately a particular value related to things like the mass of the Higgs boson indirectly. And that picture is under a lot of pressure from improving experiments. But what we don't know is it a particle / wave with a wavelength comparable to the size of a small galaxy? That's one possibility that's not excluded. Or is it a very, very small, nearly fundamental particle? There's a vast scope there for a lot of creative modifications of a simple picture, just one sterile particle, just one more thing in the list. What's different from that, though, is saying we'd like to try and explain the dark matter and dark energy observations without postulating any new content in the world, just changing the forces. That turns out to be really hard to do. When all that one knew was that the rotation curves of galaxies were wrong, you could begin to do that. But now it doesn't really hold up as far as most of the community has judged.
All right, thank you, Liam. So I was going to ask one more question of Liliana. So the question is, fear of nuclear power is understandable given the disasters that have happened and the radioactive waste. Okay, sure. Okay, sorry. So we don't have Liliana on deck. Oh, okay. So we have Liliana. Great. Okay, so fear of nuclear power is understandable given the disasters that have happened and the radioactive waste that it leaves behind. But on the other hand, nuclear power may be essential for helping us end our reliance on fossil fuels. In your fiction, how do you grapple with these competing aspects of nuclear power? You have dirty and clean, deadly and palliative.
I don't have an answer as to whether nuclear energy is the best solution to end our reliance on fossil fuels, although it's a very real alternative in a moment in which we urgently need alternatives to address climate change. But governments are responsible for the way in which radioactive waste is handled and disposed. And in my fiction, I explore how people come into contact with radioactive waste unknowingly. And in those cases, obviously, the government didn't do a good job at protecting people from danger. And for the victims, dealing with radioactive material is kind of like facing the supernatural, a mysterious, invisible force that can destroy you, and that is unlike anything else that you have experienced.
All right, thank you. So I think that closes our Q&A and our event. I'm going to thank our many presenters for the fascinating discoveries and insights that they shared with us about the science of the very, very small. And thanks to all of you for joining us this evening and for sharing your questions with us. Have a good rest of your evening and good night.